Optimizations is an applications of the derivative. In this video, we'll learn how to determine the size of a travel bag so then we can maximize its volume. Let's say an airline beta has a size limit for a jack bag of as of the sum of the width and the length and the height is at most 62 inches. All right. So the question is, if the base of the bag is a square, you have a square base, then what is the dimensions of the largest volume bag? Let's start with the volume equation, the volume formula of a bag or a box. So the volume equals to the height times the width times the length. Right? And we use notation V for the volume, H for height, W for width, and L for length. One piece of information that we know is a base of this bag is a square. That means the width equal to the length. Then we can use substitutions to substitute the length by the width. So we have the volume equals to H times width times the width. Another piece of information we have is the sum of the width and the length and the height is 62 inches. Also, the width equals to the length. Then we can come up with an equation that describes the relation between the width and the length and the height in terms of the sum, which is h plus 2w equals to 62. Originally, it should be h plus w plus l equals to 62, but we substituted l by w to get h plus 2w equals to 62. And then from these equations, we can solve for h equals to 62 minus 2w. You will see why we want to solve for h in this case. All right. We use substitution again. Keep in mind that on the previous equation, we found the formula for v, and we can combine w times w to be w squared. So v equals to h times w squared. Now we found the a formula for h in terms of w, then we can substitute the h by 62 minus 2w into the volume formula to get the formula for the volume in terms of the width is 62 minus 2w multiplied by w squared. All right, we found the volume in terms of the width. The volume is the output, the width is the only input in this function. Meaning, if we want to find the largest volume, we want to find the maximum value of this function v of w. So how to find the maximum value of a function? Given this function v in terms of w, we come up with a domain. The domain should be between 0 and 62. 0 is a positive, right? Dimensions got to be positive values, non-negative values, and 62 is the sum of the height and the width and the length. So the first task is we need to find the critical values by finding the first derivative using the product rule. We combine like terms to get negative 6w squared plus 124w, and we set the first derivative equals to 0. Then we get w equals to 62 over 3. And we get a critical value, but we're not sure whether this critical value is a local maximum or a local minimum. Then this is when you can use a second derivative test to verify this this critical value. So we find the second derivative of the function v, and we plug the critical value into the second derivative functions, which is equals to negative 124, which is the negative value. So by the second derivative test, this w, this critical point w, is a local maximum. Is where the local maximum occurs. All right, so we found it with the largest volume bag would have the width of 62/3 inches. To verify this information, we graph the functions on its domain. So the horizontal axis is the width, the vertical axis is the volume, and you can see that the local maximum is about 20, which is like 62/3. All right, gather all pieces of information together. Again, the goal is to find the largest volume bag. The conditions is the sum of the width and the length. The height is 62 inches. Also, the base is a square. And then we found the width of the maximum, volume has the width of 62.3. Then we can determine the length, which is the same as the width, and we can find the height, which is by taking the sum minus the width and the length. You get another value of 62/3 as the height of the largest volume bag. So what does it tell you? That tells you that the largest volume bag would have the dimensions of 62/3, 62/3, and 62/3. It looks like a cube, and it's actually a cube. All right. Well, thanks for watching, and I hope that this, learning this application of the derivative will motivate you to take another math course.